Hello everybody, Aaron Dahlin here. Welcome to our first experiments series. This will be a series of short videos designed to get you started as quickly as possible. We're going to breadboard working examples, briefly explain the theory, and generally provide enough information to get you started with the designs. To get you started with real-world circuits that you can build today to see that theory in practice. This particular video features the Common-Emitter fixed bias transistor amplifier. Our objectives are to introduce the circuit, to review the gain calculation and some rules of thumb that allow you to design the amplifier, and then show the performance of the circuit using a function generator and oscilloscope. Here is the circuit. It consists of a single NPN transistor, capacitively coupled input, capacitively coupled output. It has fixed bias provided by R1 and R2, and it has a emitter feedback resistor. So that's R4 and R5. We will spend some time talking about C2 and how it impacts the gain of the amplifier. Here's the circuit on a breadboard. Up here, where this red part is, that is our positive rail, which will set to 30 volts DC. Down here is the ground, and you can see that the circuit is generally laid out the same way as the schematic. R1 and R2 are the bias. Here's R1 and R2, so you can see that goes from the 30 volt rail down to ground. With the junction, that's this one right here, on pin 30 going to pin 40, which is the base of the transistor. So again, there's 30 volts, R1, and then we're going to the base of the transistor. You'll notice that this 1 microfarad C1 is also tied to that junction, and that occurs right here, which makes this header pin the input. The collector resistor is 2.2K, which is seen right here on the 30 volt rail. There is a jumper jumping across going to this point right here, which is the collector of the transistor. Here's a 1 microfarad capacitor, and this is our load, which is R6. Finally, we have the emitter, and you'll see these two 100 ohm resistors. So here's the emitter, 1 resistor, 2 resistor, ground. Later on, we'll show this bypass capacitor. Before we explore the performance of this amplifier, let's take a few minutes to consider how it was designed. Rather than going into the complete theory, I'm going to give you some rules of thumb that'll get you quite a long ways. For example, one of the first design considerations is the power supply voltage, which we selected to be 30. The next design consideration is the current, which we'll choose to be somewhere around 7 milliamps. Since we want a more or less symmetrical output from the amplifier as a function of time, we're going to choose this resistor, this R3, such that there will be 15 volts on the collector of that transistor. Based on 15 volts and 7 milliamps, we'll choose R3 to be about 2.2K. Another assumption is that we will have about 2 volts on the base, which means there will be about 1.4 volts on the emitter. If we ignore the base current for a moment, that 1.4 volts on the emitter at 7 milliamps requires emitter load consisting of R4 and R5. Another design choice is to assume that the current flowing in this bias network is 1/10 of the current flowing in the emitter. So that makes this 700 microamps. With Ohm's law, if we consider these two resistors together, we want a series resistance somewhere around 40 to 50 kiloohms. I selected R1 to be 50 kiloohms because it was convenient and I had it in stock. And then I selected R2. Using the voltage divider rule, 2 is equal to x over x plus 50k, all multiplied by 30. Solving for x, we arrive at something close to 3.6k. That's it. That's all there is to it to select those resistors. Again, we chose a supply voltage. We chose a current. Based on that, we chose this resistor so that there would be 15 volts approximately on the collector. We then chose a voltage of 2 volts. Knowing that there's about a 0.6 volt drop here, we knew that this voltage would be 1.4. Ignoring the base current for a moment, we said that we need to drop 1.4 volts when there's a current of 7 milliamps. And finally, we said that the current flowing through R1 and R2 should be 10 times less than the current flowing through the collector, which gave us a resistance somewhere around 40 to 50k. In this design, I chose R1 is 50k. Then we used the voltage divider rule to calculate this resistance right here, so that there would be 2 volts given the 50k, given the 30 volts at 700 microamps. The only thing that remains are the gain calculations and the inclusion of this capacitor here. As far as gain calculations are concerned, we'll explore the case with no capacitor C2 in circuit. We'll also explore the case when the capacitor is connected up to the junction of R4 and R5. We are not going to explore what happens when you connect the capacitor directly to the emitter, as that requires a little more math than we want to get into in this introductory video. With that said, let's calculate the gain when C2 is not installed. So gain is V out divided by V in. For this circuit, gain will be the resistance in the collector divided by the resistance in the emitter circuit. When we say resistance in the collector, what we need to do is think about it from this standpoint right here. So if you were looking out from the collector, you would see this 2.2K resistor, and you would also see this 2.2K resistor. Note that at high frequencies, C3 acts as a short. So our gain is going to be 2.2K in parallel with 2.2K all over these two resistors here, so all over 200. So the gain is 5.5. So 1 volt in will give you 5.5 volts out. Now we consider the gain when this capacitor is installed. And what happens is this capacitor effectively bypasses R5, leaving the emitter with 100 ohms unbypassed. Therefore, the gain is equal to 2.2K in parallel with 2.2K all over 100. So our gain has increased to 11. We could continue this. For example, if instead of 100 ohms, we made this 10 ohms, while keeping 200 ohms in the emitter load, so this one here would have to go to 190, then our gain would be 2.2K in parallel with 2.2K all over 10, which would give us a gain somewhere around 110. That's about as far as we can take this example. I did mention we're not going to explore it in this video, but if we were to connect this capacitor directly to the emitter, the gain would increase. But there is a limit, and that's something that we can explore in a future video. Now that we know a bit about the circuit and how it operates, we can evaluate its performance using the Digilant analog discovery as a waveform generator and this older analog oscilloscope to view the results. This is the output of the amplifier when we're feeding a 1 kilohertz signal in with a 500 millivolts amplitude. Let's go ahead and adjust that up to 1 volt. And then let's turn on the input signal. So this is the input signal on channel 1. And we can see that's 0.5 volts per division, which means there's a 1 volt positive and 1 volt negative, which is what we see over here on the Digilant waveforms display. So 1 volt amplitude means 1 volt positive, 1 volt negative. That's a peak voltage, by the way. And then our output on channel 2 is at 2 volts per division. We set this down for a little more convenience. 2, 4, 6, 8, 10. Let's call that 11 volts peak to peak. Or if you prefer, about 5.5 volts peak, which means that this amplifier has a gain of 5.5, which is what we'd expect when we have an emitter load consisting of two 2.2K resistors in parallel. So that's 1.1K divided by the 200 ohm emitter resistor. So 1.1K divided by 200 gives us a gain of 5.5. If we put the capacitor in bypassing the lower emitter resistor, the gain will increase. You can see it's increased quite a bit, and we actually have clipping. What we'll do now is we'll lower the input voltage to 100 millivolts. This is the input voltage to the amplifier, and you can see that 100 millivolts. And now we can look at the output. So let's move it here where it's convenient. So counting the gradicules, it's 0.5, 1, 1.5, 2, and we'll call that 2.15 volts, which gives us about 1.1 volt peak. We can calculate the gain by dividing that 1.1 volts out, divided by 100 millivolts, which gives us a gain of 11, which is what we'd expect, considering that we have a 1.1K ohm load on the collector and 100 ohms that is not bypassed on the emitter. So 1.1K divided by 100 gives us that gain of 11. I'm going to move that emitter capacitor one more time, and this time I'm going to place it directly across the emitter. So essentially we're bypassing both of the 100 ohm resistors. It's not very pretty, but that's the best I can do with this oscilloscope right now. We can see that the input is 20 millivolts. That's 20 millivolts positive, 20 millivolts negative. And the output is somewhere around 2, 4, 6, 8, 10, we'll call it 11 volts peak to peak, which is about 5.5 volts peak. So 5.5 divided by 0.02 gives a gain of about 275. To keep this video short, we're not going to explore why that is. Perhaps we can do so in another video on another day. At this point, I'm going to remove the capacitor and insert it so it's bypassing the lower emitter resistor. We'll turn off the input and only look at the output. Now we can see how it responds to changes in frequency. So first we'll go up. There's 2 kilohertz, 5 kilohertz, 10, 20, 50, 200, and even now the amplifier is still going strong. Let's shift to a triangle wave, which sometimes makes it easier to see the distortion. And we'll now go back down. So 500K, 200K, 100K. Here we are at 2K, 1K, 500K. And you can see something's not right anymore. Those lines curved. And at 100, you can definitely see that something's wrong. You may recognize this as capacitors charging and discharging. Stated another way, this amplifier, as built, has a problem with low frequency response. What I'm going to do now is insert 2 more capacitors. First, I'm going to take that 1 microfarad capacitor out in the input and install a 10 microfarad capacitor. And I'm also going to add a 33 microfarad capacitor across the output capacitor. You can see that the low frequency response has improved considerably, allowing us to go further down in frequency. Here's 50 hertz and 20 hertz. It looks like that distortion has returned again. We'll try one more time, lower, down to 10 hertz. It looks like we need to add additional capacitance if we wanted to reduce this distortion. Let me show you another trick that I find quite useful for identifying distortion and performance in the amplifier. We'll turn on the other channel, and then we'll shift to a mode known as the XY display. In this mode, the horizontal is the input signal and the vertical is the output. And now we can see how it responds to changes in frequency. As we go up, everything remains nice until we get to about 1 megahertz. Then you can start to see some phase shifts. And now if we go down, we can see everything is pretty good. Here we're at 500 hertz, 200, 100. You can see it's starting to open up again because we're having some phase shifts. And if we keep going, the signal is going to get smaller as the output amplitude drops. Another way of saying that is this amplifier is acting as a low-pass filter. I do hope you found this video interesting. If you have any comments, questions, or concerns, please leave them in the space below. Thank you.